paradox is to be like, well, actually, this is why motion doesn't exist because this is so complicated and all that sort of stuff. Because you got to think this is back in the 5th century BCE. So while they were great mathematicians, they don't have access. They didn't have access to all the sorts of mathematical knowledge that we have now. So, yeah, next slide. Okay, so essentially, what happened was Aristotle came after Zeno, and he was like, "Well, I don't agree with any of this, so I'm going to prove why not." So he looked into the actual theories around Zeno, and then said, "Okay, well, these are the sorts of theories that I'm going to come up with," and came up with Aristotelian infinity. So he looked into how he could split into infinity based on like division or like subtraction and addition, where you take one amount and you can consistently take the same portion repeatedly from that amount until you get down to a very, very small number, or you add continuously until you get to a really, really big number. And this was something that showed that infinity was possible. And then he went into it further and then looked at potentiality versus actuality, where potentiality doesn't necessarily mean that infinity could ever be reached, whereas actuality sort of defined it as something that was could be reached and could be completed. But Aristotle never actually believed that being complete was realistic or could ever actually happen. And this is where he sort of clashed with Zeno's idea, because Zeno's dichotomy paradox looks into how there is an end, whereas Aristotle didn't believe that. So, next slide, please. All right,
Right,
go for
sweet.
it.
So I'm going to take over. I'm going to turn my video on to do a bit of a demo. So essentially what Zeno is arguing is that motion isn't impossible because in order to traverse a distance, you need to traverse half that distance, then another half, and another half, and, ad infinitum. Um, and I've got a pretty radical proof here that motion is possible. So, just try and follow along, guys. Watch this. As you can see, pretty crazy, right? You can just walk across the room like that. That's actually what someone did back in ancient Greece. A guy called Diogenes. He was a famous cynic, right? He really didn't kind of respect a lot of the kind of over intellectualism of this problem. He thought, hey, you can just walk from one side of the room. What's the big deal? Well, is there any truth to what Diogenes does here? So if we go to the next slide, we kind of see this disparity between the world and our logic. Zeno is essentially trying to argue that what he calls pluralism can't exist. There can't be more than like one object. There can't be more than one thing, because the second we allow there to be more than one thing, there suddenly becomes infinite things. So we can't do math with them. But we still see that motion is possible. We still see that there are many things in the world. And he can just say it's an illusion. But what we can do if we want to solve the paradox is we can develop a more formalized, rigorous logic to kind of express how infinite quantities interact with each other. So if I go to the next slide, we'll just see an interval. Let's say this is the distance I want to travel, right? And I've got half the distance there and then half that remaining difference and half that. And the interval is half closed. So we've got 0 is included in the interval, but 1 isn't. And what we want to kind of argue is that the sum of the intervals in that subspace is actually equal to the whole interval itself. So what we can do is we can kind of visualize the distance that we have to go as this infinite series of decreasing decreasing values. And if we want to calculate the value at any given step, it's 1 over 2n. But also, if we want to calculate the distance that we've traveled, then it's 1 minus 1 over 2n. So now we kind of introduce the concept of a limit as developed by Weierstrass and Cauchy in the 1600s, I believe. So we want to say for a function, it's said to have a limit if when the input approaches where we're evaluating the limit at, for any small distance, it can be as small as we like, we can say there is also another small distance that for all of our input, the distance between that input of the function minus where we're evaluating the limit at is, if that is smaller than that distance, then it also implies that the distance between the value of the function when we evaluate it and the limit of the function entirely is less than another distance, delta. Um, so this can seem kind of counterintuitive, but it's in fact correct, because if we look at the function that I've graphed here using Python, we can see it's ever kind of approaching a number. And if we put p all the way out at infinity, well, we can select any arbitrarily small distances and always find that the difference between the input and the limit at infinity is, if it's less than that epsilon distance, then it also implies that the value of that function evaluated the input minus the limit of the entire space is also less than that delta. So what we can do is we can take the limit of the final partial sum, right? The partial sum of the entire series at infinity. And what we get the limit of one, which is just one. One's always going to be one. But then that's minus the limit of 1 over 2n. And that is, as we approach infinity, that is becoming arbitrarily small. In fact, it's becoming so small that we can say that as x goes to infinity, this goes to 0. And then what's 1 minus 0? It's just 1. So that proves that the entire distance when we travel an infinite series is in fact just a finite number. So what does that end up being used for? Well, that kind of key insight that Weierstrass and Cauchy had ended up being the key to calculus, right? Infinitesimals allow us to calculate derivatives, and that allows us to take distance, and then we can calculate speed and acceleration. And this gets, this blows up the math world, man. This unlocks, new insights that we've never seen before. So it gets applied in physics, it gets applied in engineering, it's applied in finance, and that's why we can do the subject we're doing today. That's the end of our presentation. If you've got any questions, please let us know. But otherwise, that's it from us.